Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 2 of the relaunch. The title is What's Our Current Path? The Titanic Table. Now, this is going to be the most important video I will probably issue on this channel. So I want to make sure that I have it as accurate as I possibly can, and as comprehensive as I can get it. Now, I originally did a version of this that I released just a couple of weeks ago when I started the relaunch. But after that, I did a series of additional videos where I did deep dives into how we calculate our temperature, how we do projections, and other kinds of things. And when I did that, I learned some new things I thought were relatively important and would help understand what I'm talking about in this message. And it occurred to me that probably a number of people, in fact, it may be most of the people who watch this video, are probably not going to go into those deep dive videos. So therefore, I thought I wanted to redo this video to incorporate the information I learned that I thought would be helpful to understand what I'm talking about into this particular redo of this video. So that's why, if you've already watched the previous video and you see a new one coming out, that's why that's happening. So let's begin. I thought I would start this whole process by just saying sort of where are we at today? And if you take a look at the upper left-hand corner, you'll see sort of an opinion survey that was done by Pew. It ran from 2013 to 2023, and then I updated it with a table on the right-hand side with some statistics. And if you take a look at that table, just take a look at the disengaged line because it's easiest to see. And you see it's at 6%, the yellow line. Now, that hasn't changed any, which is exactly what you would probably expect for disengaged people. If you look below that, though, you'll see for the doubtful and dismissive line with regard to climate change, you'll see that they've remained absolutely the same at 11% each. And that means that the group above it has really pretty much remained the same, too. The only difference is there's been a real slight increase towards alarmed from cautious to concerned, okay? But fundamentally, I think everybody's position, pretty much when it comes to climate change right now, their posture is probably pretty well closed, as is illustrated by the visual of the flower there. I want to say another thing. Today, where we live in a very fragmented media landscape with algorithmic echo chambers, and that is applicable to everybody. It includes me, probably you, etc., and includes everybody also in that list up above. And then the other thing that sort of has become obvious to me is I think most people's views on climate change are sort of formed by, what their echo chamber is, or maybe let's say what tribe they belong to or tribes they belong to. Their opinions are not based on extensive independent research, okay? We sort of believe what our groups sort of tell us to believe, our political parties we belong to, or whatever it is. And I'm going to ask you for this presentation to really try to keep an open mind and listen to what I have to say. Because my opinion, quite frankly, was framed the same way before I actually started to do the independent research. In the last 3 years, I think I've spent probably about 4,000 hours on this obsession, trying to understand what's going on with our climate and what the impact of climate change is. Why am I doing that? I'm doing it because for the sake of my granddaughters and my kids, because the more I looked into this, the more concerned I became. Now, I'm not getting paid by anybody. I don't believe in any organization. I don't even make any money doing these videos. I'm using relatively crude old Apple Mac computer. I have probably less than $200 invested in a camera and a microphone, and I'm not doing any editing of this software or anything. So that's why you occasionally see some, maybe not the highest quality slides or pages, etc., and stuff like that. But I think, I have an opinion, and I think it's formed on a very on a very sense of logic and factually based, I guess is what I'm trying to say. And I would hope you would give me the courtesy of trying to keep an open mind and just listen to what I have to say. And at the end, make whatever decisions you want to make. That's up to you. But I would ask you to sort of listen with an open mind. And if there's anything here and here you question, check it out. Go to AI. Everybody has access to AI now, pretty much. Check out anything I'm saying. So let's begin. So this is what I call the Titanic table. And I'm going to dissect this piece by piece. But let me just go through the columns here first. So the first set of columns, we talk about temperature change from pre-industrial levels. That's how the scientific community looks at it. And we talk about temperatures at 1 degree Celsius, 1.5, 2 degrees Celsius, 3 degrees Celsius, and 4 degrees Celsius, okay? The next section, I'm going to talk about tipping points, and then I'm going to talk about, okay, what's our actual temperature look like? And then we're going to talk about what the projected temperatures look like, and then we're going to talk about what the scientists say is going to happen at those different temperature levels. I just want to read a couple of those so you have the appropriate framework when you're listening to what I'm saying here at the rest of this presentation. They're saying at 1.5 degrees Celsius, we will see significant environmental, economic, and social impact. By the way, we're at 1.5 right now. At 2 degrees, they say the world will see catastrophic and likely irreversible damage. At 3 degrees, they just call it a nightmare scenario. And at 4 degrees, we say the planet is basically unrecognizable to human beings. Those are some very, very, very significant and scary words. So I want you to keep that in mind as we go through the rest of this presentation. So let's start. Okay, we'll start with the Titanic. So who's on board the Titanic? For purposes of this presentation, consider it the world's population, or about 8 billion people. So who's the captain of the Titanic? Well, I would say Donald Trump's probably the captain, but he's got a lot of senior officers that are very actively involved also. This is not a one-man show, okay? Xi Jinping from China, Modi from India, Putin from Russia, etc. And then what's the fuel for this thing? What's moving this thing really forward as fast? I would say it's probably greenhouse gases. I listed the 10 top greenhouse gas emitters. I just did a quick Google search. And you notice that most of them are state-owned companies like China, etc., and that's why they dominate the list. The United States, since we're a private enterprise system, we have individual companies. ExxonMobil make the list at number 5. But that's why if we aggregated all the United States privately held companies, we'd be much probably higher up that list also. So that's the Titanic. Now let's go to the iceberg. What does the iceberg represent? Well, to me, that represents 2 degrees Celsius, because when we hit the iceberg, it's really saying that human beings may lose the ability to prevent our temperatures from just escalating out of control. The other symbol I have there is the orchestra playing. I thought that sort of fit in with the deck of the Titanic, okay? In terms of where we're at right now, I'm not so sure they're on the deck of the Titanic playing. They might be. Maybe they're just warming up, but it is really close, folks. When I started looking at this climate stuff, I really did it because I thought it would affect my kids, my grandkids. I mean, I'm 83 years old. I can tell you right now, I think if I just live a normal life, I may see us hit that the iceberg in my lifetime. I mean, that is just frightening in terms of the implications to future generations. So let's get into now some of the meat of the presentation here. So as I mentioned before, how climate scientists do it, they have a baseline. They use anomalies. I'll talk about that when I talk about how we do calculate actual temperatures, video 4. And what you see here now is the way they look at it in terms of 1 degree Celsius, 1.5, 2, 3, and 4. Those are the sort of the frames they use And I converted it over to Fahrenheit if you wanted to see what the Fahrenheit things look like. So the question is, where does the world get all the information to do all their calculations we're going to talk about? How extensive is this information? How do we gather it, etc.? Well, it turns out that the whole world fundamentally works together to gather this information. And they do it through an organization called the World Meteorological Organization, which is a special agency of the United Nations, but it's completely independent governance and funding. The United Nations has nothing, doesn't get the vote in what they come up with. There are 193 member states that participate, territories that participate in and fund this. It's located in Geneva, and the role of this group is interesting. It's really to set standards. Sort of, okay, what are the standards, quality controls during the processes, and then they create their own transmission software or design it so that everything can communicate with one another. They have a relatively small staff. There's only 200 people involved here, and what there are is they're mostly scientists and administrators and coordinators, because all of the effort, all of the equipment, all the software development, etc., is all owned and developed by individual countries. I shouldn't say all the software. The software that they run is really developed by programmers who come from all these different countries, and they work under the coordinators in the WMO, and they also do the testing of the software, etc. And maybe give you just a sense of the scale of this. And again, we'll talk about this in video 3. I just pulled one of the slides, tables out of there, from just satellites, okay? The United States has 14 weather satellites, China 11, Russia 5, the EU 11, Japan 3, and they all their information ends up into the WMO's database. So all these countries are cooperating, and they've been doing that for decades. So when we've been at war and other kinds of things, our political leaders just can't get along. Some of the scientific communities come together and work together. Why do they do that? Well, because we live on one planet. We don't have weather systems that are only for the United States, a weather system for China, a weather system for India. We're all interconnected. And the only way, and if you want to get an understanding of what's going on, it makes sense to just cooperate together to do this. And we do. Here's just a few other things. They have automated land stations. For example, the United States has 1,000 of them, China 2,400, Russia 1,600, European Union is 4,500, Japan 1,000, and they all communicate that same information into this same central system. We have daily weather balloons that go up. By the way, there are 800 of these that go up around the globe twice a day at the same time, and to record information every 2 seconds and transmit it back into the system. Give you an idea. We have Doppler radar stations, which are all interconnected, ocean buoys, etc., and things like that. I think you get the point. Okay. Now, how do they do that? This illustration, this table here, sort of shows how this works. On the left-hand side there, you can see the various different inputs. Here's some of them. We have, by the way, we have a commercial aircraft track information. We have, as do ships. We showed satellites and other things like that. So each one of these transmits information at different times. Sometimes it's every couple seconds. Other times it's longer intervals, sort of for what makes sense for the particular area that's capturing that data. The information goes into then sort of national centers, which goes into sort of regional processing centers, and then they load the information into what we call these super centers. And there are 15 of these super centers around the globe. They're in countries like Beijing, Washington, D.C., Moscow, Tokyo, Bologna, Italy, etc. And what they do, when information gets into them, what happens is it's immediately shared with all the other systems. So everybody around the globe has immediate access to the same information. Also, the general public can get access to it. So this is not private. It's not something hidden, okay? So let's go to the next part of the table where we talked about tipping points. Now, what's a tipping point? Well, let me start out by talking about how Earth's climate systems works. There are really 5 spheres. There's the atmosphere, which is pretty obvious. That's the air. There's a hydrosphere, which is water. The cryosphere, which is ice. And then lithosphere, which is sort of the surface of the Earth and below that. And then you have the biosphere, which is living things on the surface and in the ocean, etc., and things like that. These spheres have what I call subsystems within them. And we'll talk about some of those in a second. And then these subsystems have tipping points. So what's a tipping point? Tipping point is when you change from one state to another. You're in that process where there's probably nothing you do to prevent you from changing states. Give you an example. So the Greenland ice sheet would be an ice sheet, okay? Once it hits this tipping point, it starts melting. And that melting process will sort of feed on itself, and eventually it will become a non-ice sheet. And that may take hundreds of years, by the way, given the size of this. But that's what a tipping point is. Maybe another way of thinking about it, let's think of a massive slide, okay? Remember, if you're at the top of the slide, you can get your legs over a little bit. You can even get a little bit of your body weight down the slide, okay, but you're still at the top, okay? But once you start going down a very steep slide, you're going to the bottom. And that's the same thing here with regard to tipping points. That's a way of looking at it. Now, the other thing I would say is these are massive systems. Okay, Greenland's massive. I mean, as we talk about these systems in a second. So it's almost impossible to come up with an exact tipping point. So what scientists do is they come up with tipping ranges. And so what I did here is I took all of these subsystems and listed them under the appropriate sphere. Then I went ahead and I color-coded it. So those tipping systems that will basically enter their tipping range at 1.5 degrees Celsius or earlier than that, I coded as red, because we're at 1.5 right now. Green would be those systems that would enter their tipping range when we get to 2 degrees Celsius, and black would be anything above that. Now, if you take a look at this sheet, just glance back and look at the colors. It looks like a Christmas tree, right? I mean, there's so much red and green there. Now let's take a look at the table once. You know, when we were at 1 degree Celsius, 16% of these systems had entered their tipping range. At 1.5%, and that's where we're at right now, we're at 60%. At 2 degrees, we're at 88%, almost 90% of the Earth's subsystems are in their tipping range, and they impact one another. That's why when these scientists said those dangerous things that we talked about earlier, this is why that happens. There's an acceleration that occurs here. Now let me dive into these just a little bit more so you'll get the idea. Let me break these down a little bit. So let me start out with atmospheric systems. Okay, we've identified 3 here. The first one, what they call planetary circulation engine. That includes the ITC, the Hadley cells, jet streams, etc. This doesn't have a tipping point per se. It just gets progressively worse or progressively degrades above 1.5 degrees Celsius. What that means is that actually at 1.4, or 1.5 was worse than 1.4, but 1.6 is worse than 1.5, 1.7 is worse than 1.6, etc., etc., etc. And these systems, this is it. If there was anything we talked about here, what affects our living conditions on Earth the most? Whether we have heat waves, whether we have heat domes, whether we have hurricanes, whether we have floods, whether we have massive tornadoes and other kinds of, fundamentally is determined by the behavior of that particular group of systems. It dictates our living conditions on Earth. And what are the scientists telling us? It gets worse every tenth of a degree. This is a direct correlation. Whether it's linear or accelerates, I'm not sure, but there is a direct correlation. And let me go back to now talk about the evening news, which I know a lot of people don't watch, but at 83, I'm sort of part of that habit group, okay? In 1914, in that range, we were at 1%. Occasionally, you'd see something on the evening news about weather if there was a major event. It'd be like Katrina or a major hurricane, a hurricane like that, or some other event. But most of the time, there is hardly anything in the evening news about weather. If you watch the major networks now, you'll see maybe of the actual news time, okay, which is probably 15 minutes or something, maybe 10% of that is now devoted to weather frequently. And what are they talking about? They're talking about weather disasters occurring primarily within the United States, but some around the world. And the reason it's not they're trying to sensationalize things is because those are really happening around the United States right now. But most people aren't aware of that. And that's one of the other problems we have. So let me go quickly to the next line now. And this has to do with the global thermal high-lean circulation. If you take a look at that map on the lower left-hand side there, you'll see all these circular patterns. What that tells you is that there's a circulation pattern that goes on that links up all the oceans of the Earth, and they eventually circle around Antarctica and go back. Massive heat transfer engine. The behavior of this system has a huge effect on living conditions here on Earth. It has a huge effect on it helps us out right now because it takes a lot of the current, takes a lot of the carbon dioxide and other things, especially the ocean, and moves it to the bottom of the ocean and brings up fresher water, which also helps us. It has effect on the viability of oceans in terms of living things and just a whole bunch of things. If you take a look at those, every one of those systems is in the red range. That means they've hit the start of their tipping range. Now these have large tipping range and these are very complex systems, okay? But we're there. And what would that mean with the impact of that? Just take a look at that little map there. If you take a look at Northern Europe, okay? If you sort of go across the globe, you'll see that, it looks like they're sort of somewhat equal to the Yukon territory in Siberia, right, which are extremely cold areas. Their temperatures aren't that bad. Why is that? The primary reason is the AMOC. That's how much heat transfer is going on. So let's move to the next one. The cryosphere, we've listed those, Greenland, the Arctic ice sheets, it's permafrost and other things. Let me just talk about Greenland for a second. So Greenland is already in its tipping range. It's already hit its tipping point, I should say. And so scientists say it's probably nothing we're going to do to prevent it from tipping completely. But it's going to take hundreds and hundreds of years. So what's happened as it does it? Well, it has some impacts. One, it raises sea levels, okay, which isn't good if you're an island in the Pacific or elsewhere, okay? It's slowing down the AMOC. How does it slow down the AMOC? Well, what drives a lot of the AMOC is salinity of the water. But as the ice sheet of Greenland melts, it reduces the salinity in the northern Atlantic Ocean, which then in turn slows down the AMOC. It loses some of its speed, is what I'm trying to say. What other happens is as it moves down, as the ice sheet goes down, it gets darker. What happens to that? That means it loses the albedo effect, which is the ability to reflect the white surface, reflect the sunlight back into the atmosphere. It gets absorbed in the earth, which in turn causes temperatures to go up faster. It will alter atmospheric circulations. As that ice melts, it has an influence over where hurricanes hit and other kinds of things. And it just, as you can see, it just accelerates across it impacts other ones of the subsystems, okay? The last one I want to talk about is just the biosphere. And let's just talk about the Amazon rainforest here, for example. It is the largest carbon sink on Earth. What that means is the trees there pull carbon dioxide out of the atmosphere. What's happening with it? Well, it's shrinking. Why is it shrinking? Well, part of it's, one of the reasons it's shrinking is we're burning portions of it down to make more area for farming and other kinds of things. So what happens when that occurs? Well, one, obviously the amount of carbon dioxide is pulling out of the atmosphere goes down. But the other thing that happens is that the carbon that was stored in these trees and other things goes up into the atmosphere. So not only are we taking we're taking less out, but we're putting additional amounts in. So it has an accelerating effect. Okay. The other thing it does is as the Amazon hits this tipping range and if it starts going down, it will affect global weather patterns. It will disrupt the thermal equator, the monsoon behavior of monsoons. It will have catastrophic impact on biodiversity loss and will massively affect the rest of the globe. For one other thing, I probably should mention, the Amazon is so big, it basically creates its own weather system. So one of the reasons it's a rainforest that has so much moisture is it generates so much heat and moisture out of it. It creates its own cloud system, which in turn sort of self-reinforces itself. As this shrink, it loses its ability to do that. And we're not too far from the point where it may not be able to generate its own weather patterns anymore, which will just rapidly accelerate its deterioration, which will have a huge negative effect in terms of reducing the amount of carbon dioxide it's putting out, plus putting more in. Okay. Let's move on to the next subject now. So the next subject I want to talk about is actual temperatures. And I talked about how those are calculated in video 4. And actual temperatures are really done, there's really 7 organizations that do that globally that are recognized as being credible at this. 6 of them are on the graph. China has just recently converted some of their stuff to English, but I don't have a graph with them on there. But if you take a look at the 6 organizations that do that, and by the way, they're done independently, they're in different countries using different methodologies, etc. But if you take a look at that map, what do you see? Well, you see in the 1850s there was some divergence there, but now they're all basically saying the same thing. So you have all these independent sources calculating this number and are all telling us the same thing with regard to temperatures. Other thing you'll see is this up and down cycles there. Those are primarily driven by whether we're in an El Nino or La Nina cycle. El Nino, the temperatures tend to go up dramatically and they go down in La Nina years. Now, where do they get their information? How do they calculate actual temperature? This is what Copernicus does. They probably have the most sophisticated approach out there. They measure first of all, what's happening in the temperature on the surface, but they also measure up into the atmosphere. They track all this information because that's what really influences what happens. And they basically divide the globe into cubes. And on a horizontal base around the surface of the Earth, those cubes would be 31 kilometers by 31 kilometers, or roughly 19 miles high. There are basically then, they divide the Earth into 540,000 of these cubes. Now, the next thing you have to deal with is the height. The height of these cubes vary, but they go all the way up to, they measure all the way up to 50 miles high. And they have 137 layers of cubes. And the cubes have varying heights, so, as you can see from the illustration. Next to the surface of the Earth, they're only 10 meters in high in some cases, and then they gradually increase as you go up. Why is that? Because all the action takes place at the surface of the Earth. You have all these different surfaces, right? You have oceans, you have ice sheets, you have deserts, etc., and so on, mountains and valleys and things. So you want to make sure you have you're taking very accurate small measurements of that because there's a lot of change going on there. As you move up to the stratosphere, there isn't much change going on, and so you can take a much higher cube, okay? And the reason they vary that height is it just significantly reduces the amount of math and calculations they have to do. So when that's all said and done, What that says to when they calculate weather, or what our average temperature is, they're using information in 74 million cubes. Let me say that again. To measure our actual temperature, they do that by looking at 74 million cubes of information. Now, those cubes just don't have one bit of information in it. If you see an illustration on the left-hand side, upper right-hand side rather, remember those 10 streams we have in? They calculate gather all kinds of information. So there's a lot more information put in these different cubes. You know, think of radiation, winds, temperature, clouds, heat transfer, and you can see this illustration. That's covered in the video we did in video 4. And there's also another video 6 where I go into detail about how this particular model works. Now, they do this calculation every hour. So that says there's roughly about 720 calculations a month. So every hour they calculate the average temperature using over 74 million cubes of information. That's incredible. I don't know, I hear people all the time sending me information. They will look at the temperature and back in 1982 or 1850 was higher in Phoenix, Arizona than it is today, or something like that. So therefore, climate change is real. That's not how this thing gets calculated. This is how it's getting calculated. And at this point, I just want to say one other thing. You know, you have a lot of people out there who say temperature is increasing, climate change is a hoax, and all this kind of stuff. Have you ever heard one single person who has made those kinds of statements that talks about this? This is how they calculate actual temperature? Of course not. Do they ever talk about how we captured the information we got from the WMO? Of course not. Is it secret? This old man figured it out. All this stuff, everything here that the Copernicus says is open to the general public. There's nothing hidden here, folks. So what's going on? Let's continue. Okay, so the next thing is projections. So where do we come up with our projections in terms of climate change? What happens is the Earth, the nations of the Earth, fundamentally everybody that matters on how the countries on Earth, okay, basically get together periodically. This is a massive, massive effort. The last one took 7 years. So about every 10 years now, they get together and they say, you know, we really need to figure out objectively what is happening to Earth and what does it look like our future temperatures are going to be. And they do that through something called the IPCC. That was really partially funded and organized by the WMO, the same organization there. But there are 195 sovereign nations that are a member of this group. They all have equal voting power. That means the United States has the same level of voting power as some island in the Pacific. That means the fossil fuel producing countries like Saudi Arabia and other kinds of things have an equal vote with the people that are being impacted by that. So you have this tension, which is just wonderful. But they're all doing this in a cooperative way. Why? Because we live on one planet. And we're all affected by the behavior of that planet. So they have this group is really interesting. It's only 15 people involved. They have an annual budget of about $9 million, okay? And so they're not being corrupted by big money anywhere. $9 million is pocket change to just about everybody, any of these countries, okay? And the other thing that exists, these models are done remotely across the continents, all 6 continents. There are 50 approved modeling centers was generated, but some were run more than one, so it's about 100 separate models. And to do this, when they decide to do this effort, they take experts from around the globe. Scientists and experts are nominated to this, so they select based on reputation and skill set. And it's not just client scientists, it's modelers, it's economists, it's archaeologists, it's experts, the kinds of experts you do, urban planners, the kinds of experts you'd want to have involved in looking and making these assessments. And the other interesting thing is individual countries, just like the WMO, pay for all their participants, okay? And then they go through, so the AR6 went through this 7-year process. In 2015, they sort of scoped it and did the foundation. But that means that the models that generated these climate change have to be pre-approved by everybody, and they have to run through a set of tests to make sure that they're accurate. And every country that does that gets a chance to watch what every other country is doing to share their results are available, source codes available, etc., so they can really verify that their models work. And it's only after that a model is approved that it's allowed to participate in this process. And once that's approved, it's locked down, so it cannot be changed. And then what happens, they all get fed the same scenarios. And then after those are done, they have groups that go ahead and they create the peer reviews, and they have a first draft, then they do a final draft, and they go through the 100, and I'll talk about that a little bit more later. The preliminary sort of goes through and approves the report, and they issue the final report. Okay, so here are the 5 scenarios that everybody ran. And you can see they went from very low emissions to low emissions to middle of the road, high and very high emissions, okay? And as a result of that, they came up with different times as when we'd hit different temperature levels. Like at 1.9, they said we'd hit 1.5 degrees Celsius in 2035 and never crossed beyond that because we leveled off there. The low emissions one would hit 2 degrees Celsius at 2050, but never get any higher than that. The third scenario said we would really get the 3% sometime, but the model said between 2065 and 2080, and get the 4% after 2100, and then the rest of it is, and I highlighted the bottom one here, which is, so for each one of the columns I showed the ranges. That's what appears in the table that we showed you previously in terms of when they projected we were going to hit that particular timeline. I took the highest and the lowest numbers here and said that's the range that these models came up with. Now these numbers, I got to tell you, are based on a 20-year moving average, so they're not that sensitive, okay? And what they do, that says we have to be, the 20-year moving average has to have crossed 1.5 degrees Celsius before they're reported. Now they do one other thing here is they take the midpoint of that. So when you see 2030, that means that was the midpoint that said between 2020 and 2040, the model in 2040 finally hit 1.5 degrees Celsius. So therefore they took the midpoint of that as saying when we crossed it, which would have been 2030. Now the other thing I want to talk about are these reports, or what the assessment, I guess is a way of saying it, that the scientists come up with. So they really have working group. One group works on the models. They have 2 other groups that work on this assessment stuff, sort of what happens at these different temperature levels. And what they do is they come together, there's thousands of scientists that get nominated. They select hundreds of them to participate in this. It's all done by the preliminary. And then what they go ahead and do is they do the research, and then they create a first draft. And then what they do is that draft is then subject to independent review. And so anybody that wants to can look at their report and submit a comment or critique. And every one of those single critiques has to be responded to, and it's done in writing, and all of that, the question, what they said, what the response was, what the critique was, is all made available to the public. Then after they get through that process, they create a second draft. That second draft, and it comes in sections, okay? It goes before the plenary of this 195 nations. And they then work on the final approval of that. And every single line, every sentence in that report needs to be unanimously approved by this group. So that means you have obviously people with different interests. You have people that are the fossil fuel producing countries have one thing they want to say, and you have island nation that's going to be flooded by this that has a different opinion. So, I mean, they all have to agree before it makes the final report, and they do that. And the other thing that happens is that they give the scientists then a final veto on that. So if they all agree with something, it comes down and saying, wait a minute here, I know you all agreed with this, but that's not what the science says. The scientists have a video and say, no, that's not what the science says. Go back and try again, you know. And so when you see this information here, see these numbers here, these aren't some obscure scientist somewhere or some guy at a university doing this. These are the experts from around the globe. This is vetted by every single nation in the world. So I think this is about as reliable of an explanation as you can get. Okay? That is the process. And all of this is also available to the public. And I showed you a copy of the assessment. So back to the Titanic table again. So now I've walked through the Titanic table and the various different columns and how we got there. What I wanted to do is show you how these numbers are calculated, the kinds of information involved, so you can understand the integrity of these numbers. I mean, as I look at this, given our fractured world, this is probably the best you could expect for the human race to do to come up with something. And it's interesting when you hear the climate skeptics talk about this stuff. Oh, this is a hoax or whatever. You never, ever hear any of them talk about the process. They don't talk about where the data is collected. They don't talk about how it's calculated. They have over was the 74 million cubes of information that we're doing on an hourly basis to calculate actual temperature. They don't talk about how all the scientists of the world participated in these projections and these assessments. Why? It's all available to the public. And I want to say one other thing. If you take a look at this table, if you go to the observed 9, and you can see we went up 9 degrees. We went up a half a degree in 9 years. What I did in that roll is I said if we can continue at that pace, based on that actual number, we would hit 2 degrees Celsius in 2033. We'd hit 3 degrees in 2051 and 4 degrees in 2069. The models are not as conservative as that. I think the models actually said, for example, we wouldn't hit 1.5 degrees Celsius until somewhere between 2030 and 2035. Now, their number is a 20-year average. The 9-year thing was based on a 1-year average, so that you have some of that distortion going on. But the other thing I say, these models are just naturally probably conservative. Why? Because they're based, the whole process to produce this report in 2023 really probably started on scientific information 8 or 9 years before that. And so as a result, they don't have a currency to it. I'm going to talk about that in a separate video I have also. I'll talk about where these models are maybe too conservative or can't keep up with the pace of change that's going on. So let me wrap this up now. So we talked here about where we got the information. I talked about the Titanic table and why, from my individual assessment of looking at this data, why I think the numbers they presented are credible, the message they're getting out is a little bit too conservative, and why I think we're going to have we could hit 2 degrees Celsius fairly soon, within 10 years. And the other thing I want you to understand is why I'm so passionate about this and why I'm concerned for our kids and for future generations. This data is real. It is accurate. It's probably as best human race can do in terms of putting this stuff together. It is incredibly thorough. And it is a worldwide effort involving the scientific community around the world. These aren't some people in some think tanks, one person, some special interest group someplace else. This is the whole world community doing this. Let me end with the only way we're going to prevent a climate crisis is we've got to get to net zero now greenhouse gases. And we need to do that now or as fast as humanly possible. And the last thing is, this video is getting very long, so let me wrap this up fairly quick. What I really think is important is that our political leaders aren't going to solve this problem, folks. At least our current ones aren't. So what we need to do is vote in every election for candidates who believe this is a crisis, because it is, and have the personality to work together with other people to solve this problem, because we need to solve this as a human race. If you found this video interesting, subscribe, rate it, share it with other people. And thanks again for spending your time doing this. And just have a great day.